Hello? I guess you can hear me. Good afternoon, everybody. Traditionally, this is the toughest talk, the one right after the lunch. So I'll try to do my best to keep you awake, even though they took the coffee away. So sorry, couldn't get that organized. My name is Sergei Larin. I'm presenting today with my coworker, Aditya Kumar. He's going to offer the support mainly. And we are here to talk about the topic we already spoke 2 or 3 times in past 2 or 3 years, but hopefully this time is going to be different. We're actually going to do something about it. So originally, it was introduced as a buff, and the whole layout of the presentation is more suitable for two-way conversation as opposed to presentation. So please feel free to interrupt me at any time. If you have questions, comments, or if I say something I shouldn't, just let me know. And let me try to state what we are trying to achieve here. I want to reopen the conversation and share some experience about global scheduling in LLVM. And I want to take it one step further away from just scheduling. I want to see if the global scope processing, for the lack of a better word, can benefit us widely, not just for scheduling, but for any other transformations we can think about. I'll try to cover that throughout the conversation. And I want to open the conversation on possible changes to the infrastructure, maybe even additions to the IR that might help us to accommodate all the changes we're talking about. So if that is clear, that's what we're doing. Let me start by talking about conceptual scheduling steps. There are multiple ways to look at simple problem. The way I think about the scheduling process is in a series of major steps that only fraction of which is theoretical time accurate for a statically scheduled target. Because instruction scheduling is notoriously sensitive to the order of things. So when you register allocate versus when you schedule, when you do machine-specific optimizations, when you don't. We in LLVM and we in Qualcomm trying to use that infrastructure residing to distributed scheduling. So instead of having a single pass that would produce optimal order of instructions, we do it in 4, sometimes 5 different steps. So the course milestones is before the register allocation commences, so pre-array scheduling. That's where the currently machine instruction scheduler is most commonly used. And after yesterday's presentation by Dave about subtarget addition to a MI scheduler, I don't have to repeat the history of that piece of code, which was very conveniently done back then. Register allocation, obviously, takes it a bit further. And post-register allocation scheduling is supposed to take care of things that register allocation broke. Obviously, there are passes in between and so on, but we're talking about in very coarse grain here. And finally, for those targets that have to statically assign timing, or bundles in our case, there is usually a special step, bundling or packetization or finalization of bundling. And then there could be more additional steps, but we'll talk about a little bit later. So at least this is the timeline I would like you to keep in mind as we talk about it. So distributed instruction scheduling. Each step has its benefits and its drawbacks. Before register allocation, obviously, you have the most flexible representation of your code. It only have true data dependency most of the time and control dependency, so the most flexible. So if you see scheduling as moving instructions up and down, putting them in a proper order, that's where you do at least constrain. But at the same time, you can get carried away very easily, so you have to anticipate the register pressure that you can create by doing so. If you have too much parallelism available and your scheduler too aggressive, you will quickly run out of the registers physically available for your target, and you will have much worse code if you wouldn't do scheduling to begin with. Today, when instantiate a VLIW scheduler, it's one of the many flavors, and I'm sorry, I have VLIW background, that's what I'm most comfortable talking about. It has its own way to model the timing for each packet. So we have what's known as DFA model of timing, which answers me, okay, which instructions I can issue in the same cycle. The irony is, within the scheduler, I use it widely to figure out which instructions go when, but then I discard it totally. I basically drop all that information, and I don't recreate the timing accurate model all the way to the back end. Why it's done so? Simply speaking, because the rest of the flow of the compiler, all of those steps I was talking about, don't understand bundles too well. The bundle support was introduced a number of years ago, and declaratively, each pass should be able to operate upon them. If you look at the original implementation, bundle viewed as an atomic instruction, theoretically. But the thing starts getting trickier when you introduce, for example, predication inside of your bundles. Then a lot of things break. First things breaks, that's the liveness analysis. It's not necessarily doing incorrect thing, but it's doing it so conservatively that it defeats the purpose. The next complication is that there are some passes that people wrote and I would like to use, but they don't have a concept of a bundle. And they simply break or core dump. I've seen all kinds of things that they were never tested with bundles to begin with. I will come back to that idea again and again. So the bundle information is basically dispersed. I just drop it. And finally, all of the current implementations of the instruction scheduling done in the basic block scope. And that's why we're talking about it today. We want to extend it. The second big scheduling step is a post-array scheduling. So at this point of time, we're dealing with physical registers. We've already introduced our spill and fill code. And we, in general, trying to deal with that additional inserted instructions to maybe organize them in some better way. At this point of time, we can introduce bundles much less painfully, for example. But again, given the today's state of the code, there are still passes between that point and the code gen that just don't support, in very much the same fashion, don't support bundles the way they should. Again, liveness becomes even more a challenge at that point of time. After register allocation, liveness and predication becomes a serious issue. And the final step that is currently in the flow is finalizing of the bundles. After that, many assumptions are broken, and at that point of time, not many more passes are expected to be operated upon the code. So we're pretty much free to do whatever our backend wants. So one of the examples I would be talking about today is how we introduce a custom global scheduler at that point of time, very late in the game. And the surprise, actually, surprise in a good way, was that it recovered a lot of performance. So simply speaking, I have a current distributed infrastructure. I schedule twice or 3 times. I do all the optimizations. At the end of the day, I do more global scheduling, and I'm recovering performance. How much? Some test cases are obviously outliers, and I've seen 10%, and I've seen even more. But on a spec int 2000K, we've recovered, 1.4% on average. The good thing about global scheduling, it tends to be non-heroic optimizations, if you know what I mean, if you remember Chris's talk several years ago about heroic optimization. It lifts everything. It affects every kind of code. It's very general. It's not specific to certain pattern of a code or a certain loop. So it helps little bit everywhere. But again, for the purpose of my analysis, what I'm saying, well, there is still some performance left on the table. And doing it so late is more as a cleanup as opposed to a strategic approach to scheduling in the serious compiler infrastructure. So I'll repeat myself a lot. When I say global scheduling, what do I understand by that? First of all, first step is forming a scheduling region. At this point of time, anybody who is targeting a target that does dynamic scheduling in the runtime says, I mean, what's the point? Okay, I have the hardware that perfectly well does any kind of crisis resolution on the flight. If I have a stall, I issue instruction and so on. It's true, and there are many things you cannot anticipate during the compile time, but if your scheduling scope during the global scheduling is larger or substantially larger than the scope of your hardware that's dynamically trying to reorder things, theoretically, you can do a better job. Now, think outside of scheduling. Scheduling is just reordering instructions. Think about peephole. Running a global peephole, let's say my peephole looks for multiply and add or something else and tries to come up with a new instruction. Doing it on a global scope yields a better code. So if I can perform a peephole on multiple BLAZY blocks crossing boundaries, it should help me. Have nothing to do with scheduling. It has nothing to do with VLIW. It's generally a good thing. So there is a whole class of optimizations that can benefit just from that entity that's called region. Again, jumping ahead of myself, today we have passes that operate on functions. We have passes that operate on basic blocks. We have passes that operate on modules. But between functions and modules, there is something else. There is a formalized region, depending on what you want, which kind of region you want to do. And you can have run on region kind of pass. That's when it connects to IR, right? We don't have to change the IR to accommodate a region. LLVM today have region forming class, which forms very simple traces. And I think the original purpose of that was for profiling, if I remember right. So the region, if you just grab for keyword region with capital R, you will already find some code that does that. But we're going to go a bit further than that. So depending on what kind of regions you're talking about, there's traces, superblocks, hyperblocks, regions, those of you who know what I'm talking about. We can have an analysis pass that says, okay, here's the function, partition it into regions according to some assumptions. And during that partitioning, one of the most critical or important things is to grab as many basic blocks into a region without having to duplicate too much code. Again, depending on what kind of region formation you do, you can choose to having no code duplication whatsoever, to duplicate every single tail of a tree, create a tree region, which creates a lot of code duplication but gives you the biggest freedom. Well, hope you have a big registry file to support that. So complex if conversion becomes a part of region forming. And that's an important mental point to make. Again, I will come back to it. When to do it? Well, I don't see a case doing anything in SSA. So as soon as we left SSA and before we start messing with the DAG, it looks like the earliest and most convenient time to have the first region forming support. So technically right in that big course scheme of things right before the register allocation where the MI scheduler right now lives. To form an accurate region, you do need accurate profiling information. We've gone, as the LLVM community, we've gone a long way in increasing the precision of statically available profiling information. We can have dynamic profile information, but regarding which way you do it, if you don't have an accurate profile, region forming might actually hurt you as opposed to help. And again, the trade-off would be, if you don't allow code duplication, maybe it's not such a big deal. But immediately, we're going back to liveness. If we introduce a complex if conversion, if we introduce a bunch of predicates into code, is the liveness going to work? Is it going to give me an accurate answer? How is that going to help? Next level of complication, cyclic, acyclic scheduling is usually done quite differently. The exhibit number 1 would be software pipelining. So if I perform software pipelining, right now I tend to do it very early in the game. For all the same reasons, software pipelining is scheduling. All the same reasons for least constraints and most close to the original intent of the code. Software pipelining can do very serious transformations. It's ironic that today it's done so early, and for the same reasons I've already called out, the bundling forming is not allowed. You can form bundles, but then you cannot send them down the pipeline. Some of the passes will barf, and register allocation will not work properly. So all your accurate tuning, all your II calculations, and all your careful layout of that code will likely to be dispersed, then put through a meat grinder of all other optimizations, and then somewhere close to the code gen, you have to recreate that originally carefully scheduled loop with timing, with bundling, without having any information flow, whatever the intent was originally. And you just hope that your packetizer bundler will get it right. But beyond that, the interaction between cyclic and acyclic scheduler, some compilers take that loop out of consideration of the rest of the optimization altogether. You don't even compute liveness into it. It almost looks like an abstracted region with in and out data flow, and you don't do any transformation at all. Does it look like a region on its own, of some sort of specialized region? For me, it kind of does. You say to the compiler, here is a region that is a black box. Please don't do anything with it. If you are describing a region on the level of the compiler support, one of the most useful things, like we do it on bundles today, we expose liveness information to its boundaries, right, to the top level. So you don't have every time to go inside of the bundle and calculate the liveness inside of it. Naturally, if we choose to do a region support, it should be able to do the same. It should maintain liveness on its, in edges and out edges, and should be readily available. I don't need to recalculate it again. So, okay, again, if we have a cyclically scheduled loop, maybe call it a region, have liveness around it, and treat it specially. Auto-vectorization, I'm not even getting there. I'm not going to be done. If there is some auto-vectorizations, being performed, some CMD transformations being performed in a loop, maybe, okay, again, it's some kind of a region. Okay, let me move on. Defending what I'm forced to do today, performing global instruction scheduling, instruction moving after register allocation, very late in the game, has its benefits. For once, you cannot make things worse. You're very unlikely to make things worse. You already have your critical path set in stone and register allocated. So doing it late, you don't have to worry about introducing register pressure. Simply speaking, if you don't have an available register, you don't do a transformation. But you still can significantly improve your original code, and not just on a simple scheduling like making the critical path short. I've seen some research trying to reduce the power consumption during the creative scheduling. Once your critical path is set, you can choose to delay execution of instructions to certain positions where they less likely to cause power spikes or something like that. Okay? Same thing, you can have machine-specific peephole optimizations. My architecture supports a lot of those, so it's non-trivial consideration for me, but doing that peepholes depends on the presence of bundles. So sometimes I can, instead of 2 instructions, produce 1, but only if they're in a packet with some other instruction. So those rules become very, very restrictive, very creative. So doing it late, Once everything is already kind of in a machine instruction level, it has all the physical registers, it's much easier. And having nothing to lose but your chains, those of you who studied Karl Marx should understand what I'm talking about. I don't think that's a huge portion of the crowd, but okay. The negative side of it, obviously, you cannot really talk about meaningful region formation. You're too constrained for that. You can play within the bounds of existing, okay, these are the cards, you play with them. Yes, you cannot do some creative things and your scheduler becomes rather complex. Finally, which I encounter very quickly, it tends to create multi-way branching. And I'll give an example today. As far as I understand today, it's a heresy inside of the rest of the compilers. So if you have 2, 3-way destinations after a basic block, it's going to break a lot of assumptions. The promised case study. So I already said several times, I spoke a lot about how we do that. And I will try to go through a quick example. But the important points, we do it late. We do it with a custom liveness analysis because we couldn't do it any other way. And it performs speculative predictive global scheduling using superblocks. So here is a small example. This is actually taken from a real loop, from a real benchmark. And it shows the code as it arrives to almost all the way to the end of the code generation. So it's after the packetization and after the processing. And bear in mind, this is 4 wide issue machine we're talking about. And between the parentheses is basically one bundle, one packet. So you have 1, 2, 3, 4, at least 4 cycles execution time given all the stalls and everything. And you have some control flow. This is actually a loop. And the blue bar around here delineates a superblock. So you have single entrance and multiple exits. So our code, the first thing it does, it tries to pull an instruction from basic block 3. I'll try to point it if it will work right here. So this is a load word. And it goes repeatedly, scans the code, and it says, well, OK, it actually can be executed in basic block 1, pull up, right? Because there is some available space in there. I already have 2 packets. Oops. So I have 1 packet, 2nd packet. And I have an instruction that I can actually, from here, pull in there and execute it for free. It's the same cycle. I'm not going to lengthen my critical path. It's already set in stone. But if you try to do that, that's where your liveness kicks in and says, well, look, if you do that, there is an R2 use right here. So it's live in into basic block 2. And you cannot simply perform that. So we go and split the live range, in essence. And we scavenge for a register. R7 is available. And we put the R2 value into R7 and substitute the use of it right here. So suddenly R2 is not live anymore, and I can pull the load. Now, here is the important thing. Pulling a load in general might be dangerous for 2 reasons. Once, you might execute a load that you otherwise wouldn't execute. And if you see in this code, that load is not predicated. Even if you predicate a load, it still might cause a trouble if it's, for example, unmapped area of memory, right? If you would never execute it because the branch would never leave you there, but you have done it speculatively and it caused an exception, well, you just did something not very good. But the trick we played here, the optimization was, if you can see the 2 loads are actually accessing members of the same structure. So it's R2 and R2 plus 4. And the logic goes, well, if you're accessing one element of a structure, you can't presume that you're safely able to access the second element of the structure. So we play that trick, and that's probably one of the most, that creative things that are happening here. So, OK, basic block 3 now is an empty block. It's jumped through. So you can easily, well, actually, no, I'm ahead of myself. So before that, I continue to aggressively try to pull things up, and I see that the copy can be pulled up. Then, okay, if this is my region, I want to move as many things up as possible. I try to speculate the load, again, the one that we already moved up, but now I predicate it. So predicate is available. In our architecture, you can use predicate in the same bundle or in the same cycle as it was set. That's the .new. So this packet here is now full. It performs two predicated instructions. It compares its own predicate, and it performs a copy. So fast forward, I already gave up the thing about the basic block tree, that it's not needed anymore. You can completely eliminate it. And performing the same steps two more times, we end up with only two basic blocks, only 3 cycles, 3 bundles, and a 3-way branch at the end. So again, in my architecture, you can have multiple branches with the same bundle. They're going to be executed left to right. That's perfectly fine. And there is a fall-through path after that. Well, needless to say, if this code is seen by any of the passes, it's not going to work. But that's just an example of what you can do. It's not a full-blown schedule. It's a cleanup pass. It's a pull-up pass. And it just gives you some feel to it. The important points. And again, I already touched on several of them. We had to reduce, we have to focus on simple things. We did super block formation, not hyperblock formation. We did simple things first. Machine verifier pass was very instrumental in achieving working code. It needed to be taught how to deal with predication, not surprisingly, because right now, machine verifier will not do many things, so it has to be massaged a little bit. The big thing, we had to implement our own liveness analysis. Okay, and that's the major thing, and that's the major thing that needs to be improved if you want to move anywhere. And we still, it's still an ongoing work. I guess that's my final statement. We can easily perform bundling along with that, but we don't do it right now. A more generalized infrastructure should definitely help. So this is the part of the talk when it was supposed to be two-way. Okay, so up till now I was describing an example and general infrastructure, but here is a bunch of questions, not necessarily all of them have answers. The simplest on the surface implementation is have the region information as an analysis pass. You give it a function, I guess, and you have a collection of regions coming back at you. All of that, special processing is performed, it's hidden. It generates the liveness on the region boundaries. So it gives you that information. It's ready to use. And if we have some kind of support for it, it does not have to be repeated again unless you change something within that region. So hopefully we don't do things twice unless we have to. Can we have a completely autonomous pass? Yes, definitely. That means we don't introduce the region into the LLVM. It's totally invisible for the rest of the compiler. But then, as I said, we'll have to do that thing again and again. Every time I want to form a region, I'll have to repeat that word. So having IR support, I'll start to speed up a little bit. Having an IR support would definitely help. Another example, if you ever want to go back, like reversive conversion. So if you've done something and you say, well, okay, it didn't work out quite well until later, and I really rather do it differently now, then you can choose to, disassemble that region into regional components. Having that information stashed somewhere along with the data structure that helps you to do that, again, might be either enabling you in the first place to do that because there are some irreversible transformations during if conversion is possible, or at least speed it up significantly. Finally, there was a big discussion on unbundling. So if we introduce bundles rather early in the pipeline, and let's say I want to insert an instruction in a bundle because my pass decided that certain things need to be done, can we always deterministically go from parallel semantics to serial semantics? And I was prepared for this discussion. My take is yes, you can always do it. But there could always be an architecture, exposed pipeline comes into mind right away, that once you go to parallel semantics, you might not necessarily be able to go back. The capital example is a swap case, right? A equals B, B equals A. To go back to serial semantics, to disperse a packet like that, you actually need a temporary storage. And if you're late in the game and you don't have a scavenged register, that might prove tricky. There is such thing as an XOR copy. It might work, I don't know. It should be theoretically quite doable on a register level because XOR copy only gives you incorrect answer if A equals B. Then you have 0 instead of a swap. But because you're at the point you're dealing with the physical registers, hopefully that you can deterministically set, well, no, you can do it. But then there are some cases where we might not be able, and I leave it open. In my architecture, I can always disperse a packet if I have to. I can always take a single instruction out of the packet if I have to. But if somebody have more discussion on that, I'm definitely willing to hear it. The last bullet on this slide, almost never you have to do it. It's a rare occasion. It's highly speculative. The people who've done that told me that, well, do you really, really ever have to do it? But at this point of conceptual introduction, I don't know. Okay, maybe somebody somewhere needs to do it, and then we need to provide support for it. I just, kind of want to put it out here. Profiling in 4. I already talked about it, and without precise profiling in 4, we cannot really form regions. If my customer is unwilling to do the runtime profiling, full-blown profiling, if I'm reduced to static prediction, ball and Laris might not be enough. Maybe we need to have some kind of ball of tricks. Maybe we need to have some kind of machine-specific hooks to provide clues about certain instructions. These instructions always appear together and they always produce that kind of result. Some architectures have built-in prediction on a jumps like we do, so it could be pulled into that structure as well. Register allocation and presence of bundles is a very interesting concept. Technically, register allocating on bundles is better. Think about live range that ends and starts in the same bundle. So you can physically use the same physical register up to this bundle and from this bundle, and it will be, less constrained. You just suddenly have a little bit more overlap on the live ranges. Today, I don't think it works, unless somebody tells me otherwise. And if we take it to absurd, some people talking about conjointly register allocating and scheduling. I don't know if we're there, but I just thought I'll throw it out there. Maybe somebody wants to discuss it. So I have like 3 more slides very quickly. Predicate-aware liveness, already said it. That needs to be done first, if we want to move from here, and that's where we can use the most help. Bundle-aware passes, so passes shouldn't break if their bundles are passed into it. Some improvements to register coalesce are definitely needed. Support for memory speculation. That's the only, or any unsafe instruction, that there should be some API that says, well, I can speculate this instruction, or I can speculate this instruction if it's predicated, or I cannot do it at all. Okay? GCC had such a support, so we can discuss that. Instruction selection can be altered based on the presence of bundles. I can select different instructions, and if I do it early enough, maybe something works out there. More of a long time, long term, get that entrenched. I'll just skip. If you want to read this, I'm out of time, so I'll try to finish it quickly. And eventually, big ticket items, undoing things. So if your scheduling didn't work out, you statically know that your result is worse than you would do otherwise. So maybe, have alternative scheduling solutions for some critical portions of code. Global deconstruction determinism, I foresee some issues there. And eventually full pre-register allocation bundling support. That might include things like predicate fees, SSA with the fee form, with the predication form. But that's really long term. If somebody wants to talk about, I would be happy to entertain them. So that's pretty much it. If you have any questions, I'll happily try to answer them.
Any questions?
I was wondering if there's basically something analogous to a phase ordering problem in the sense that once you've identified a scheduling run, you can then say, well, here's the region that would be optimal to use, with the pass manager, but you won't necessarily. You can make some guesses about that, but it may almost be an iterative process to come up with a region.
So basically saying, I'm rephrasing your question, but I can statically know the outcome of my scheduling before I emit it, right? So backtracking, yes. And on some architectures, it's easier than on others, but theoretically, when I was playing with the VLIW scheduler, I would produce 2 alternative schedules and then compare which one is shorter, and it always wins. So you can have theoretical differences, but yes, it's definitely possible. For statically scheduled architectures, it's very useful.
Well, since you say you're happy to talk about pre-RA scheduler, so yeah, I would like to ask you. First of all, I think in a number of VLIW architecture, when they did their transformations and scheduling, they typically do the pre-RA, right? So
I agree.
As a matter of fact, doing the post-RA cases is a rarity until here.
Right.
So if we do have a long-term plan, or if we do believe that's a better approach, because now you put us a long-term, right? If you have done everything you have done here and near-term and mid-terms, when you get to a pre-RA, you have to redo a lot of things here.
I know.
So is a kind of ordering of doing things the right way to protect your investment?
It's a benefit cost analysis, right? I mean, the further I go upstream, theoretically, the better result I get, but more work has to be performed. That's why I'm talking about it publicly, and I actually want to make people aware of, we are doing it one way or another, and we're doing it bottom up kind of thing. But yes, you're absolutely right. It's a lot of changes to a lot of things. But will they be beneficial for outside of VLIW and scheduling? That's what I begin with. If you're talking about global scope optimizations, traditional optimizations in a grander scope, maybe it's worth investing. GCC doesn't do it. Many compilers don't do it. And if we do, then we have a competitive edge.
Hi, so I want to return to your concept of regions. And I think that a lot of architectures would that can do predication fairly cheaply or easily, would benefit from the creation of regions that, combine conditional and unconditional blocks together, for example. But it would be great to have some kind of a poll of, because I'm not sure how prevalent that is. I mean, that may be, well, I guess if it's not beneficial information at all to some people, but there might be a way to abstract the rules by which those regions would be created from the collection of that rule,
It's in a big way, it's a function of your code, and it's a function of your target.
Exactly.
Because, if I have only 4 predicate registers on my target, having aggressive hyperblock formation is not for me.
Yeah.
And very quickly, we'll have to spill predicate registers.
Right.
So yes, and that's why having infrastructure as opposed to one size fits all, that's the approach of, we take an LLVM for many things. That's one of them.
Yeah. So I guess part of that is abstracting the methodology that
Right.
people want to employ
Right.
from
Right.
the actual region collections
Right.
themselves.
So,
Two more
one more
questions.
question.
Hello. Could you speak a little more about the benefits of combining this pass with the register allocator? A combined instruction, scheduling, and register allocation pass appears in the literature, and there are some challenges with that. It would seem to resolve some of your redundancy issues. There's liveness analysis, et cetera. And would you remind me, does this still require a run of the current MI instruction scheduling pass before register allocation?
No,
or does
it's not,
this
it's not
supplant it?
required. No, it's not required. You can run MI and issue instructions in the same order. I don't think it's required.
All right.
So yes.
So back to the original question.
Right.
Yes, thank
That's
you.
a research topic, right? And I'm afraid there is no single answer. It again depends on your architecture and the kind of code that you're trying to deal with. In my case, it's going to be highly beneficial because my code generation depends on the presence of bundles. Again, my code selection, right now I have a whole slew of peepholes that try and after fact combine instructions into new instructions like post increments and so on. And if I can do it at the same time as I'm register allocating, I'm going to be much more optimal. I know that for sure. Is it true for everybody else? Sorry, can't tell. But it's a function of what you're trying to accommodate. I think we're out of time. Please, come and.
So let's give thanks to our speaker.